Okay, so what we're doing now is we're going to run this notebook from top to bottom, make sure everything executes, and please go make sure everything's consistent. You're going to check it for yourself. There are some duplicated cells. Oh, the stuff I need to delete. It's explanation stuff. This is usually what happens. Start explaining stuff, modify, and then forget to modify it back. Okay. What is happening here? Number of elements 3. Why is this now breaking? What? See where things are going wrong. Value shapes 1, 3 and 1, 3 is not aligned. Dot. The XD tie. So we can then transpose this maybe. That's the issue. Okay, so what I did was I just put a transpose here. Let me just explain this quickly. Maybe break it again. So we can use this as a lesson to learn for the debugging. So what you see is here, here is the issue. It says the dot product between the end, psi, and local coordinates is trying to do a dot product between 1 by 3 and a 1 by 3. That can't work. So we need to take a dot product between a 1 by 3 and a 3 by 1. So that's why this local coordinates are put transpose to make it a 3 by 1. And I do that, everything is hunky-dory. Okay. Where is this? Okay. So just bear in mind, this is, if it's not running on your side, how that happened. Okay, maybe change it, playing stuff and explaining something at some point. Okay, got to change it back. So first off, let's look at the characteristics here. So I'm going to first do the 2-element one. So let's do a severe case of 2 elements. Let's see what the response is for this example. This is now example of this uniaxial tension. Area is large here and tapers down smaller there. So initially the problem was slightly different, but now you can see it's sort of this consistent kind of area. But what I just want to talk about is just a couple of the characteristics. You can go about and check that these values make sense from the previous tutorials. That's something that you can go double check for yourself. But what I want to talk about is that the displacement, again, with its prescribed, is exactly satisfied. And what we see is that this displacement field is not discontinuous. What I do see here is indeed that if I look at the strain field, there's a jump there. If I look at the stress field, there's a jump. If I look at this internal force field, I can see essentially that there's sort of places that is continuous, but it's not smooth. Okay, so this is what we observe here. So this is just important to take note. And what we see is essentially that these humps are, if I look at this base there, it goes from 150 to 975 for a single element. For 2 elements. Okay, so and we will make it a single element and see what happens to these ranges, and make it more and see what happens to these ranges. But what I wanted to talk about is it my expectation that the displacement field is continuous, but that the strain field can have a jump, can be actually discontinuous? So although it looks like it's actually discontinuous there. Okay, so just the plotting that makes it look like there's a stop fill there, but this is really discontinuous, and that is also discontinuous. Okay. So my question is should the displacement field always be continuous? And the answer is yes. And the reason is, at this element, so I've got this element here, and I've got this element here, I am sharing a node. So the displacement of this element at this node is that node's value, this node is that node's value, this node is that node's value. For this element, it's the same nodal value. So there can't be a gap or anything. It has to be continuous for the displacement field, because this element shares a node, and the answer of what the displacement of that node is the value of that node, and that's the same between this element and this element. And the reason, so what you have to understand is by construction, the displacement field will always be continuous. If you see discontinuous displacement field and you do standard finite element methods, there's a problem. Okay, something has gone haywire. When it comes to the strain field, why can this thing be discontinuous, and why is that completely okay? And the same with the stress. Why can this thing be discontinuous, and why is that okay? Well, the reason is simple. And the reason is as follows. For this element, I'm taking this nodal displacement, and this nodal displacement in isolation, and as a post-process step, I'm computing the strain of this element, independent of anything else. It's just this value, and this value that will dictate how the strain field will look. Okay, and in this element, I'm taking this displacement field, this displacement to dictate how this strain field will look. But the reality is, the change of the strain field here will affect what's going on there as well. And so there's no enforcement that the strain must be continuous at this node at all. The only thing that we use is these three values for this element to compute the strain, and these three values to compute the strain for this element. And there is no enforcement that the strain must match up at those points. And as a matter of fact, the fact that they don't match up is a very good thing, because it tells you, the larger this gap, tells you that maybe you should refine, you should have more elements there. If the gap is small, it says to you, well, you don't have to really maybe refine that much. It's already the discontinuity is not that much. So that's actually called adaptive mesh refinement. It's one of the strategies that's very often employed to mesh a FEM, and that's called a posterior adaptive mesh refinement. And I'll maybe put up a video showing you what it is, or some pictures of what it is. Maybe what I'll do is I'll put one of the papers up that talks about adaptive mesh refinement, using these errors to show you more or less that you can refine and say automatically, without the engineering involved, saying the gap in the stress field and the strain fields here is too much, this discontinuity is, let's rather put more elements down. So, but there's no requirement that the strain field or stress field must be continuous. In simple example cases, it can be continuous, but it doesn't have to be. That's important to take note of. And the internal force field that we see here is essentially the sort of relationship of where we are taking this stress and we're multiplying it with the appropriate and associated area. So that's essentially what we're doing to create our internal force fields. Okay. As a matter of fact, this is actually where this one is, and there's a gap there. This is a fake thing there. This is actually discontinuous as well. This internal force is, as with the stress, it completely can be discontinuous. This is, as a matter of fact, that's where that internal force ends. This is just an artifact of the way we're plotting, because we are just plotting a lot of nodes between each other. Maybe what I'll do is I'll change the see if I can change the plotting. See if I can change the plotting to rather be just the dots as opposed to the lines. Where's that plotting now? FEM problem. I just want to see if I can rather, because at the moment we are plotting. This is the stress field, internal field, and what I want to do is I rather want to just plot it as dots, so you can see for yourself what's chopping here. I can't recall now what is the, and what you see is this is, let me make the dots finer, put some more resolution in. Where was that again? This was, element fields. That's the resolution per element field, that's defined. So where do I find here? So where do I call the element field? So resolution per element. Resolution per element. Number of elements and the resolution per element. Where do I call that? In here, I'm specifying the cable nodes. Let's check yes, number of elements. Number of elements, this is what I get out. See here. Resolution element, there it is. That's what I was looking for. Okay, so let's make it 51 or 101. Okay, so let's do that. Go crazy. And this is just what to show you that there is this one internal force discontinuity, and there's the other one. Okay, and I can do the same with making these other ones also plotting rather the dots as opposed to the lines, just to show you what's chopping here. So that's that, that's that. That's that. And now when you do this, you can, so that's already circles. That's fine. I want to just show you more. Ooh, what the hell happened here? Ah, my apologies. I can't put it there at the end. I have to put it here before the label. And that comma is extra. It's a redundant one. There I can put it. There I can put it. Just you can't put a keyword after a label has been placed, so just take note. So what I see here is there's this, and if I zoom in here, can we zoom in properly? No, it's going to be hard. No, I can't. I'm not going to be able to zoom in properly there. But there's this one line, there's a jump there, and there's the other line. That's really what we see there. Okay. I can maybe just try one more thing. I want to label the point, but I just may say, let's say one thing mark size equals 1. So you can see there, as you zoom in, there's the one, the jump, and then there's the other line. That's what you can see there. Okay, but it's also clear here from the internal force that there's a discontinuity in the jump there. So, my apologies. Sorry, I've got no chance to mute. Sorry for that. But this is essentially what we see here when it comes to these elements. And now what I want you to just observe is, as I make the elements more or less, what happens to this range. Let's look at the internal force to keep it there, so that we can focus on what is this internal force. It's expected to actually see just as 1,000. That was a loading applied. Okay. So 10, 15, 975. That's sort of the range we have there. Okay. If I make it one element, you can see here 920, 1040, much larger range. Okay. So that's the one that you've seen before. You know that one more or less. And now I can go and say, let's make it now 2 elements again. That's just to remind you that 975, 1015. Let's make it in 4. Let's double the elements as we go along. So 4 elements. Look at that range now. 992, 1004. This is H refinement in action. Okay. And again, there's discontinuities and stuff. But look at how much tighter it is around 1,000. Now let's go. 8. Look at that range. 998. 1,001. Can you see that? Still a little bit of craziness there, but look at how smooth these things have become. Look at how this has become. So again, I'm still using quadratic elements, just lots of them. Okay, and look at these responses now. Look at this. Look at this displacement field. Look at our strain field. Look at our stress field on top of the exact answer. Okay, beautiful. That's really approximating quite well. And still, there's small discontinuities there. Don't make a mistake. There's definitely still some small discontinuities there. And I can go on and say, let's make it 16. And now I can see that is 1,000. That's this range. So I just want to see how to read this graph. There's a plus 1,000 here. So it's whatever is here, it's between minus 0.6 and 0.2 plus 1,000. So it's essentially 1,000.2 to essentially 999.4. That's essentially the range that we see here. That's a plus. See a plus there, plus 1,000. Look at that. You can see that's essentially now. Look how beautiful things are converging. 32. Look at that range now. 0.15, 0.05. Okay, look at that response for the internal force. And you can see things are converging stunningly. Okay, so let's go crazy. Let's make it 1,000. Why not? Okay. Ooh. Okay. Look at that. 1,000 plus, look at that small range. Okay, plus only that small range. Look at that. The complexity of what you're seeing. And now you can see beautifully there is that approximation and the exact answer is essentially the same. And this is the finite element method. Take a complex problem, break it into something simple, and now we're just using simple fields. We're using really nice and quadratic fields, elements, but we're using 1,000 of them over this 1 to 0 domain. So hopefully this gives you a really good idea of what the finite element method is all about, and that what H refinement is about. P refinement would be if you go from a linear to a quadratic to a third order to fourth order to fifth order element. Typically that's not done. You typically stop at quadratic elements. That's typically what you want to use, and then we rather use lots of them. Okay, so that's really the go-to message for this part of the course. So please go and play with this code, and also I want to encourage you, please, to go and see what the time is. Yes, I can stop this now. Please go and try to see if you can modify this code to be a linear element. This is a good example for you to play with. Let's make this a linear, working as for linear elements, and then see the difference between the two. This will be actually quite fun, changing this to become a linear element. If you have time and you want something to really make sure you solidify a little bit of what's going on here, please implement the linear element on your own volition. Okay, great, thanks. I'm going to stop and I'll have one last video that I'll just quickly talk about one or two aspects.